So in the previous set of videos, I focused on the aspect of the equilibrium constant. I focused on like the activities aspect, so how composition affected the equilibrium constant. What I want to focus now is how temperature affects that equilibrium constant. And the relationship with temperature and the equilibrium constant is going to be through the exponential term that had that delta G of reaction in it. Okay? All right, and so to get a better understanding of the temperature dependence, what we're going to do is we're going to rearrange this equation so that we have natural log of K on the left-hand side. We have delta G reaction over RT on the right. We're now going to take the partial derivative of the natural log of K with respect to T. So we'll do that on the right-hand side too. Okay. And by definition, if we're taking the partial derivative of a Gibbs energy over temperature with respect to T, that is going to give us a negative enthalpy over T squared. Right? And if you're not sure why or how I did this, see Chapter 7 for the derivation. Okay. In any case, what we have now is that this derivative, d dt natural log of K, is going to be equal to, these negatives cancel with one another, over RT squared. And so, if we integrate that, we integrate d ln of K, that is going to be equal to the integral of delta H reaction over RT squared dt. And so I'll call this reaction 1. Okay? Now this equation that I'm calling reaction 1 can be a bit tricky, especially if you actually want to take into account changes in heat capacities between the products and the reactants. Okay? And so there's a long derivation to show that. But what I want to focus on now, at least to keep things simple for the end of the year, is that if you run into a situation where there's a similar number of moles on the reactant and product side, and each species involved in the reaction each has a similar heat capacity, then this delta H reaction here, you could actually just treat that as a constant. Okay? And so, once again, delta H reaction is generally not a constant. But if you run into the situation where all these things are true, then you can treat it as a constant. Okay? And so that means that if we go look back at equation 1 here, we treat this as a constant, pull that out of the integral, and then what we would get is ln of K at some temperature over K at some, perhaps reference temperature, T naught. That's going to be equal to negative delta H reaction times 1 over T minus 1 over T naught. Okay? And typically, your T naught is defined as being room temp, or 298 Kelvin. All right? You could also rearrange this equation just a little bit. So that you have ln of K at whatever temperature you care about is equal to negative delta H reaction over R times 1 over T plus delta H reaction R T naught plus ln of K at some T naught. And the reason I wrote the equation like this is because now we have a linear equation where if 1 over T is our x variable, then the slope is something that would give us that enthalpy of reaction. And then all this stuff over here, these are all constants anyway, so this would be the y-intercept. Okay? All right, and we could visualize this reaction or this equation, using the following plot. Okay? So on this plot, the y-axis is going to be ln of k, x-axis is 1 over t, and we're looking at inverse temperature here, right? And so on this axis, to at least orient yourself a little bit better, if we're at a low value of 1 over t, then what we're looking at is a high temperature. And if we're looking at a high value of 1 over t, then what we're looking at is a low temperature. Okay? All right, and now, if we go back to this equation, we have our delta H reaction here, and it's multiplied by a negative sign. And so what we want to look at is two different cases, okay? If our delta H reaction is going to be positive, so if reaction is positive, and it may be easier if I just reproduce that equation on this slide. So I'm going to copy this. Just post it up here. Oh, I don't have enough room. Let me move this down a little bit. Okay. So we have this equation here. All right, and so once again, if our delta H reaction is positive, but our slope, this equation has a negative sign in here, we essentially are going to have a negative slope. And so as we increase 1 over t, we're going to see a negative slope, right? So, or another way to think of it is as we increase the temperature from low temperature to high temperature, right, we're going to see that our equilibrium constant is going to increase, right? And that's products over reactants. And so as we increase the temperature of the system, we're going to see more product, right? The equilibrium be shifted to give us more product. Conversely, let's now think of the case where delta H reaction is negative. Okay? So here, if it's negative, if this is negative, then it cancels out this negative. And so as we increase 1 over t, we would see a positive slope like that. Or in other words, as we increase temperature from low temperature to high temperature, we would actually see a decrease in the equilibrium constant, and we would see more reactants produced. Okay? All right, and so just to, it's kind of a counterintuitive thing, so I just want to, write this out. And so for a delta H reaction that's greater than 0, essentially what we're saying is that this is an endothermic process. Okay? And so if delta H reaction is positive, then for our system, heat is actually treated as a reactant. And so when we increase temperature, you can kind of think of it as we're increasing heat, right? And so since heat is a reactant, the more heat we add, the more product we're going to get. And so as a result, the equilibrium constant is going to go up. Conversely, if delta H of reaction is negative, that means we have an exothermic reaction, right? So as the reaction proceeds, it's releasing energy. Or in other words, heat is a product. And so if we are increasing heat, we're increasing temperature, we're adding to the product side, and so there's less of a driving force for the reaction to proceed. And so as a result, the equilibrium constant will decrease. All right, and so these things I'm all saying, these are things that you have probably seen before. Or in general, the things that I'm saying are actually some of the core tenets of Le Chatelier's principle. Okay? And so this is actually where this comes from, where Le Chatelier's principles were derived from. It's coming from, this concept of equilibrium constants here.